Hi guys, welcome back. In this session, we are going to take a look into how to trace function calls in Windows using x64 DBG. Essentially, what we are trying to do here is we are trying to see if our functions has been hooked by an EDR or not. What kind of EDR protection DLLs are put into place? What kind of DLLs has been injected by the EDR in a given process? Okay, and what kind of functions, what all functions has been hooked as a result of that injection? So before diving into the hands-on part, I would like to give you a brief overview of what function hooking is in a very layman terms. So I believe almost all of you would have explored burp suit, or they have used burp suit at some point earlier. So essentially what happens is burp suit, whenever you send some data while testing web applications, you send that data from your browser. Before that data reaches the server, it goes through the burp suit. Okay, so burp suit acts as a proxy, and you can effectively manipulate the data in the burp suit. You can see the data in burp suit, and you can forward the data to the server. And similarly, the server replies back, and it is up to you if you want to see the data here in the burp suit, or if you just want to relay the data right to the browser. The same principle happens in case of function hooking as well. What EDR is going to do is EDR is going to inject its own DLL. Okay, so its own DLL is going to be injected, and that DLL is going to act as a proxy to all the function calls. So whenever your application is going to make a function call, this DLL is going to sit at the edge of the kernel mode. So this DLL is going to act as a proxy to all the function calls. So whenever a function call is going to be made from the user mode, before that call is transferred to the kernel mode, that function call is going to be relayed through the injected DLL. So I'll just clear this thing up. So what happens is, let's say we have user mode here, and we have got kernel mode here. And this is like, you can say, the DLL, the EDR, the DLL which has been injected by the EDR. So whenever you make a function call, what happens is multiple backend DLLs are called, multiple DLLs are involved. From one DLL, from one level to another level, slowly you transition from user mode to the kernel mode. Eventually, at last, you make a syscall, and something happens inside the kernel. Okay, whatever operation you want to do. But in case of function hooking, what happens is when you make a function call, the function all the parameters are going to be passed to the injected DLL, and then that DLL is going to inspect. So just like in burp suit, you can inspect the HTTP request. Similarly, what DLL is doing is DLL is going to inspect the injected DLL by the EDR. It's going to inspect all the parameters, all the function call that is being made, and it is going to see for any sort of anomaly. If everything looks nice, if everything looks fine, that is going to be passed ahead, and that is going to be successfully executed. If not, it is going to be blocked right here. Okay, so that is a high level overview of what function hooking is. I'll create a separate video diving deep inside how you can hook functions by yourself, and we'll take a look into some sort of an open source solution to look into the code base, how this happens technically. In today's session, we want to see if, let's say, there are multiple functions here. So there can be multiple functions that an application is going to use in user mode. Let's say there are multiple functions like fun1, fun2, fun3, and 4, so on and so forth. So this DLL is not going to hook all of these functions. It is only going to hook some of these functions that has some sort of bad reputation. Those functions which an EDR thinks that these sort of functions can be exploited by an attacker, only those functions are generally hooked. So let's say function 2 is hooked. So you call a function 2, and that function is hooked. So, and the call is relayed through the DLL. Now, in this session, we are going to take a look into how we can identify that which function is hooked. Out of all the functions, we are going to trace which function is hooked, how unhooked function looks like, and how a hooked function looks like. Okay. All right. So for this demonstration, I am going to take a look into the write process memory function. Okay, it's a very well-known function that is utilized in process injection. I have given a short write-up of process injection here on my LinkedIn, and you can see write process memory function is used by the attackers when they are trying to write something, okay, at a specific location in the memory. All right. I have a sample code base here as well that is a POC for process injection, and you can see write process function has been implemented here. Here is the Windows documentation for write process memory, and we can see that this function is part of kernel32.dll. Okay, so exported by kernel32.dll. Okay, if you want to take a look into the arguments, you can see what all it takes. It takes a handle to the process, etc., etc. I'm not going to take a dive into the arguments for now. All right. So this is the function which has a bad reputation. If there is an EDR in place, there is a high probability that this function is going to be hooked. And we are just going to take a look into how we can check this thing. So for this demonstration, what I'm going to do is I am going to open up a notepad. So what I'm doing here is essentially I'm creating a process. So this is a naive process. This is uh, a harmless process, okay, that is running. And I'm going to open up my x64 DBG. I'll attach this process, notepad, okay. I'll go to the symbols tab and I'll see all the DLLs which are available, which are being utilized by this process. So let me just move it a little here. All right. So we can see a lot of DLLs are being utilized by this process. So let's search for kernel32 and I can see kernel32. Oops, I accidentally double clicked on it. So this is the kernel32.dll and these are all the functions which are being exported by this DLL. So I'm going to search for write process memory and I'm just going to double click on it. So once I double click on it, it is going to take me to this kernel32.dll and we can see here, if we take a look, it tells us that I'm currently inside kernel32.dll. This is the text section. This is the beginning of the text section of this DLL. Okay, and the same can be seen here as well. And I can see that a jump to this function is being made here. Okay, so let's jump then. So I'm trying to trace this function call. So I'll jump. Let's double click on it. When I jump, you can see that I have been taken to kernel base.dll, and this is the address of this .text section. Okay, and what I'm going to do is I'm just going to scroll here looking for some sort of process memory, write process memory function. This is the beginning. Okay, you can see the one which is highlighted in the red. All right, I can see query virtual memory. I'm scrolling and here I can see ZW query virtual memory, and here I can see NT write virtual memory. So NT, whenever you see a function starting from NT keyword, this is an indication that NT API is being called. Okay, now we are transitioning to the NT API. So I can see a call is being made to this function, NT write virtual memory. So it is the NT API equivalent of write virtual memory function. So, all right, so let's double click on it. Once I double click on it, you can see that I have been moved to ntdll.dll. So now I'm inside ntdll.dll. This is the beginning of this text section. And here I can see that here you can see NT write virtual memory function is being invoked. How it is being invoked, basically, I can see the syscall stub here. So whenever you see these sort of instructions, this is like a standard set of instruction that you are always going to find whenever there's going to be a syscall that is being made. So setting the stack right, preserving the value of RCX register. We are moving the value of RCX register into R10 register, and we are moving the value 3A into EAX register. Okay. And then we are making a syscall, and then we are doing a return. So what is happening here is essentially, and for not only this function, you can see for other functions as well, for all the other functions as well, you can see a standard pattern that is being made here. Whenever you are going to see a syscall, before that, a syscall stub is going to be formulated. It's also known as, you can say, function prologue. Okay. Every time you will see preserving the existing RCX register, every time an RCX register is going to be preserved, and the value that you see that is moving inside, that is being moved to EAX register, this value 3A, this is known as syscall number. Okay, this is essentially what is syscall number. This is also known as system service number, or SSN. So there are multiple names. These are all synonymous: system service number, SSN, or syscall number. So now we can see, we know from this debugging that 3A is the syscall number for NT-write virtual memory function. Okay, and this is what is being loaded in the EAX, and then a syscall is going to be made. So there's a standard calling convention that you need to know, that whenever a syscall is going to be made, what is the calling convention? Calling convention. And the calling convention varies from the architecture to architecture, from different assemblies. Okay. All right. So I'll take few minutes to talk a little bit about these syscall numbers. When this syscall is being made, at that moment, the control is transferred to the kernel mode. Then the kernel is instructed that what kind of operation needs to be performed. That is being controlled by the syscall number. And the kernel knows that when it receives this system service number, or SSN, what it needs to do. Okay. All right. So at this point, I'm going to take some time to talk a little bit about syscall numbers. These syscall numbers are something which are very crucial for any red teamer or malware developer or offensive security specialist. These syscall numbers vary from operating system version to version. For this, I have this very good website, that is J00RU or Joru. And you can come here, and we have documented the syscall numbers of different functions across different versions of Windows. So you can see within Windows 10 itself, with the different versions, you will see that the syscall number is going to change. Okay, let's take an example. Let's just search for NT write virtual memory. This is the function we were talking about, and you can see 0x3A, 0x3A. This is with respect to Windows 10. Okay, so if I just go all the way to the top, yeah, so we are inside the Windows 10 section, and this NT write virtual memory, this syscall number previously was 0x37. Somewhere between it was 0x38, then it was 0x39, and then 0x3A. So Windows do not document these things. There is no official documentation by Windows for these syscall numbers. The agenda is that Windows don't want you to know what syscall numbers is. It's essentially a sort of security feature by Windows. What Windows allows you to do is that it has this Windows API that is the last layer for the developers. So whenever you want to do anything, whenever you want to interact with the Windows kernel, you cannot do it directly. What Windows has offered is Windows has offered this Windows API, and they provide you with heavy documentation for Windows API functions, and they expect you to utilize these functions and not utilize the syscalls. It is nothing but an abstraction layer around the syscall numbers. Okay. So now we have seen how does a normal syscall looks like. So I'll just take a screenshot of this for your reference. I'll go to the paint. I'll paste it here. So now what we are going to do is we are going to trace the same function call inside an operating system where an EDR is in place. So I have moved into my Bitdefender box, and here I'm going to start Notepad. So I've started this process, and I'm going to start x64 dbg. All right. So now in my x64 debugger, I'll attach this Notepad process. All right. And similarly, I'll go to my symbols table, and in here, I'm going to search for kernel 32, and you can see it's right here. And I'll search for the function write process memory. I'll double click on it. And here you can see the similar steps are going to be followed. I'm inside kernel32.dll. This is the address where we are, the color which is highlighted in red. This is the place where write process memory function call is going to be made. For this, it is going to make a jump to this function. So let's double click on it. And it takes me to the kernel base.dll. Inside kernel base.dll, if I just scroll it a little, just a food for thought, you can see these strings on the right hand side. BDHKM is API and DLL imports. Okay, this has some meaning, but I'll just leave this thing for your curiosity, for your food for thought. So now I'm scrolling here looking for some write virtual memory function, and I can see NT write virtual memory function. A call is being made, so I'll double click on it, and now I am inside ntdll.dll. Okay, and this is the text section, this is the place, and what I can see here is there is something unusual here. If I just take a screenshot of this, and if I go back to the paint, and if I bring both of these things parallel to each other, you can see this section that here, this is how a normal syscall looks like with a syscall stub. Okay. And when I see here, before a syscall, I cannot find that syscall stub. Although I can find a syscall stub for other function, but I cannot find that syscall stub here. So it is absent here, it is present here. So this is an indication that this function has been hooked. This function is not hooked by the DLL because it is making a legitimate syscall, you can see here, but this function has been hooked. It is taking me to ZW write virtual memory. All right. And how do I know this thing? Because the function prolog or the syscall stub is missing. That's one thing. And there's a hard-coded jump instruction that is being made here. So we are jumping to a hard-coded address. Okay, this is the address in the memory where we are going to make a jump. So this is a very big indication that this function would have been hooked. All right, so let's go ahead and trace this thing. Let's double click on it. I double clicked on it, and you can see that we are lost somewhere. Okay, you can see in this pane, bottom pane, I cannot find any DLL. All right, if I just so this grayed area is the place where we are currently now. Okay, so here it is going to make some essential changes, aligning the stack, preserving the existing addresses for returning from this hook. Okay, let's just ignore it for a while, and then I can see a call to this address is being made. So I'll just double click on it. Okay, so again I'm at some place, and again I can see these strings on the right hand side, bdhkm something something. All right, just scrolling here. Okay, let's see. I can see another call here. From here we are making a call to this address, so let's double click on it, and now I can see that I have landed inside this bdhkm64.dll. Okay, I have landed inside this DLL. So while tracing, we found that we have landed here at this place. And what is this DLL? This is not a standard DLL. You cannot find anything around bdhkm64.dll in Microsoft documentation, at least. Okay, this is not official Microsoft DLL. So where is this DLL coming from? Let's go back to symbols table, and we can see, we can search for this bdhk m64.dll, and we can see that yes, indeed, this DLL is present. This DLL is being included as part of this process, and it is present in C program files, Bitdefender, endpoint security in this so and so folder. The name in itself is giving a very big hint that it is a DLL of Bitdefender. This is a DLL which is provided by Bitdefender, and essentially I'll tell you that this is the DLL which has been injected. So let's go to C program files, Bitdefender, endpoint security, bdhkm, and we can see this is the DLL that has been injected by the Bitdefender. The file description in itself tells us that this is Bitdefender hooking DLL. And if I just go to the properties, just some look into the, let's say, digital signatures, I can see it has been signed by Bitdefender. It has been signed by Microsoft Windows. That is a bit odd, but that makes sense. So essentially this is sort of a protection against EDR bypasses, which was introduced later on. So there's a whole lot of information that is going to be covered around this in a later session. All right. And essentially we have traced the function call, and we have concluded that write virtual memory function was essentially hooked by the Bitdefender using the bdhkm64.dll. Now there's a very interesting thing around syscall. To bypass this function hooking, there's this direct syscall technique which is utilized by malware developers. What they do is, instead of making a call to write virtual memory function or anti-write virtual memory function, instead of making a call to these functions, because whenever you are going to make a call to this function, it is going to be proxied via this Bitdefender DLL, and you don't want to do that. So what malware developers do is, to bypass the EDRs, one of the ways to bypass function hooking is using the direct syscall numbers. So what they do is they identify the syscall number which is relevant to their function call, and they directly make this syscall using this number, using this SSN. Okay, And this is a very, I would say, I won't say a hard technique, a hard way of bypassing EDR, but I would say a very specific way to bypass EDR. Because why do I say so? Because hard coding system calls is going to introduce the issue with platform dependency. Okay, your malware may work with a specific version of Windows and it may not work with another version of Windows. Okay, so the portability becomes an issue. You cannot utilize it for a wider spread. You cannot utilize it across the different versions of Windows. Okay, so this was just one of the technique that is used for avoiding function hooking. There are different techniques that can be utilized for function hooking, and in the upcoming sessions we are going to take a look into how we can use these direct syscalls for EDR evasion, how we can hook functions. Generally, function hooking is also utilized in rootkits. Okay, when you are trying to create a rootkit, you heavily rely on function hooking. Okay, in this video, I'm not going to go into the details or the explanation or the logic behind how stuff is happening. And the agenda is to trace a function call, to identify if a function is being hooked, and if it is hooked, then what is the DLL that is being used to hook that function, okay, or to proxy those functions. So as usual, I'm going to open up my x64 DBG and I'm going to open up a notepad process. I'm going to attach this process into my x64 DBG, and I'm going to go to the symbols tab and I'm going to search for kernel 32. So here it is. In here, I'm looking for write process memory function. So I'll double click on it. Once I double click on it, I can see that I'm currently inside kernel32.dll and the same steps that we have already followed for tracing the Bitdefender DLL. So let's jump. I'm inside kernel base.dll. I'm going to scroll a little and I can see NT write virtual memory. Let's double click on it. And finally, I have been provided with this ZW write virtual memory function call, and I can see the syscall that is being made here, and I can see that the normal syscall stub is not present here. Okay, so ideally we see that before making a syscall, EAX register needs to have the syscall number. So you can see this is the normal syscall. So you can see this function and the syscall stub is fine. Okay, we can see that syscall number 3 base moved to EAX, but for the case of ZW write virtual memory, we can see that our register EAX is not being pushed with any syscall. So it can be clearly seen over here. Okay, so this is essentially an identification that this function has been hooked. As we can see that there's a jump to an hard-coded address. So let's take a look and let's follow along with this address. So I've been jumped inside NTDLL itself, and further here I can see another jump to another hard-coded address. Let's jump, and here you can see that I have landed inside this UMPPC 17706.dll. This is something unusual. This is not some sort of a standard Windows DLL. Okay, so we'll take a look into this UMPPC 17706. So let's go to our symbols table. UMPPC 17706.dll, and yes, indeed, it is being imported. So let's see, this is the path. Let's open up this DLL. So I can see that it is present in C Windows System 32 UMPPC 17706.dll. Once I hover on it, I can see the file description. It says it's a CrowdStrike Falcon sensor support module, company CrowdStrike.inc. So this is also an indication that we have successfully found that this is the CrowdStrike Falcon sensors DLL, and yes, this function has been hooked. And if I just go to the properties and check the signing here as well, you can see that this has been signed with CrowdStrike INC. So this is another indicator that this is essentially the DLL that we were looking for. Okay. All right. So now let's take a look into the Sophos EDR, and let's try to identify how functions are being hooked, what kind of pattern is being utilized in case of Sophos EDR, and what is the DLL that is being utilized by Sophos. So as usual, I'm going to start up my x64 debugger. Let's open up a notepad process, and let me just increase the font size for this. So I'll go to view. Where is it? I think it's an option. Yeah, appearances. Let's increase the font size a little for your legibility. All right, let's attach notepad.exe, and let's go to symbols table, and let's find kernel 32, and I can find the kernel 32.dll here. Let's search for write process memory. Let's double click on it. So I can see I'm inside kernel 32.dll. Let's jump and follow along. So I'm inside kernel base.dll, and I'm looking for the write virtual memory function. Here I can see a call to this function. So let's follow along with this call. And here I can see the syscall. And when I see the syscall, you can see that before the syscall, the EAX register is not being filled with the syscall number. So for this function, I can see that syscall stub has been manipulated, and I can see that there's a jump to a hard-coded address. Just for your reference, this is how a normal syscall stub looks like. Okay, we can see a normal syscall number being pushed to EAX and a syscall being made. All right, and here I can see that it has been manipulated, and there's a jump to this hard-coded address. So let's follow along. Let's jump. I jumped to this address, and I can already see some hints to HMP alert. So this is going to be revealed in a while, in a very short while, you can see. So there's another jump to this hard-coded address. Let's double click on it, and I can see that I have landed inside HMP alert.dll. This is another non-standard DLL that is not provided by Windows API. So let's go to symbols and let's search for HMP. So I can see that this DLL is present here, and let's try to see where it is present. So let's go and take a look. So I can see it is in C Windows System 32. The DLL name is hmpalert.dll, and when I hover on it, I can see in the file description it mentions that it is being offered by Sophos Limited. And just like we have a Falcon sensor for CrowdStrike, similarly we have Hitman Pro for Sophos. Okay, so it is clearly visible in the file description as well. So we have successfully traced DLL, and you can see that it has been indeed signed by the Sophos Limited. All right, so that would be all for this video, and let's catch up in another one.